Without further ado, we're going to get going today. And there we go. We got a stream. And we have a stream. All right. So when last we met, we went through lesson B, where we talked about pure substances and mixtures. And before we even talked about that, we talked about particle theory. So I want to do just a real quick kind of 2-minute version of a reminder. Who can tell me what particle theory tells us? What does particle theory mean? The idea behind particle theory is what? Yeah. Yeah, good. So everything is made up of matter. So everything around you is made up of matter, and we define matter as anything that has mass and volume, takes up space. Good. And so the idea is that if something is matter, if something has mass and takes up space, it is made up of.
We didn't hear about it.
Sorry?
Tell first, I'd like to see if we can borrow 2 computers.
If there's any on the rack, they're yours. If you can make sure by the end of the day you bring them back for me, that'd be great. Thank you. So, if we were able to zoom in on any of that matter that takes up space and has mass, and get close enough and close enough, or if we said the idea, if we keep cutting it in half, what would we eventually find? What would we eventually get to? Sorry? Yes, an atom. Good answer. I'm going to just quickly get this door, just because I'm sure I'm annoying them. No, go on in. That's fine. If you got work to get caught up on, this is actually a good time for it. Yeah, so all mass is made up of atoms. So we have individual particles that if we zoom down to, we see. Now, those particles are really, really, really small. And what are they always doing? They're always moving. They're always in motion. And what can you tell me about that motion? What can you tell me about the motion of particles? What do we know? Yeah. Good. So if a particle is moving really fast, we call that heat. Something is hot if its particles are moving quickly. And if something is cold, its particles are moving slowly. Good. All right. So that's the basic idea there. And then we said that can also explain the states of matter. Why would something be a solid in terms of particle theory? What is happening to those particles if we call it a solid, like this table, or like my skull? My famously solid skull. Yeah. Sorry? Yeah, so what are the particles doing in a solid?
No.
They're moving, yeah. They're moving, but how are they moving? Yeah, kind of in place, right? We said for a solid, you can think of it as like a person you sit next to who's always shaking their leg. Always in motion, but staying in one place. Does that make sense? What it really means is that as those particles are moving, but they're not moving fast enough to pull away from each other, because there's always a force of attraction between the particles. What happens when we heat a solid up enough that those particles start to be able to move a little bit freely of each other? They become able to partially overcome those forces of attraction. What do we call that state of matter? A liquid, good. And then finally, when they are able to move so fast that they can pull completely away from each other and basically move totally independently of one another, what do we call that? We call it gas. Very good. Does that basically make sense? Nice. Wow, I think that's my first time reviewing a concept this whole year, because it's my first time teaching the same group of people twice in a week. Normally we do a lot of this. From there, we got into the idea of pure substances and mixtures. And I don't want to get too far into this, but I thought it would be nice to just see if we remember the idea by taking a look at some of what were the homework questions. So let's do that. So we then said, based on what those particles look like, we can classify material. So if I looked at pure water, and we said everyone knows what water is, right? Water has what formula? Yeah, that's right. It's made of 1 oxygen and 2 hydrogens. Everyone knows that. So if I have pure water, how would we classify that matter? We would say it as what? Is it a pure substance or a mixture? Sure, so it's definitely a pure substance. And then would we say an element or a compound in this case? Compound, good. What would it have to look like if it were an element? What would it have to look like if it were an element? Yeah.
It would have to be like one specific type of
Yeah, specifically what are they called? What are each of these smallest possible particles called? They are called atoms. And if this were going to be an element, it could only have one type of atom. This is a compound because it's a set recipe. They're always stuck together the same way, but they're different types of atoms. We have hydrogens and we have an oxygen. Good. Does that make sense? All right. What about aluminum? Does anyone know, what would we classify aluminum as?
Pure.
Okay, it's pure. So aluminum are all the same particle. And then is there such thing as an aluminum atom? Yeah, there is. And you can always Google that. If you look for aluminum atom, you'll find something comes up. We're going to talk about the periodic table on Monday of next week. You don't have to know it yet. Don't worry about that. But yeah, this is all aluminum atoms. You would find an aluminum atom here, an aluminum atom there, an aluminum atom there. They're all going to look the same. So what do we call that? Sorry? Yeah, it's an element. Good. I want to go over here because, again, I don't want to go through all these. Over here we had pure water, and we said that's a pure compound. What about tap water? What about tap water? Oh, you guys are so quiet today. I think I may have unintentionally taken the contributors out of the room. Look at this. What do we think? Tap water. Ah, okay. You're right, it's a mixture. Because when you take water out of the tap, is it actually just water? No, there's other stuff in there, right? There's stuff we add on purpose. You ever heard of fluoride? We treat our water with fluoride because it's good for your teeth. So we figure since people need some, that's a good, safe way to make sure everyone's getting some. So we put it in there. But it also has just minerals in it, right? There's some calcium, and there's some magnesium, and there's some iron. There's just stuff in there. So it's a mixture. Now, having said that, what kind of mixture is it? What kind of mixture is it? Good. And why is it a solution? Because you can't see the different parts. What's another word for that? We can say it's a solution, or we could say it is... I heard it. It is homogeneous or homogeneous. Good. Those mean the same thing. Homogeneous just means the same throughout. Same throughout. And we'll look at one other one, salad dressing. I'll leave the rest to your wonderment and cleverness. But salad dressing, what would we say? I mean, depending on what you put on your salad, but I think if you just go to like the grocery store and buy, the kind of like Italian salad dressing that's like an odd color of yellow, where you're like, should food be that color of yellow? That's really yellow, but you eat it anyway because it's pretty delicious. Are we all picturing that in our head? Do you know the one I'm talking about? It's got like little orange bits in it, and little white bits and little green bits floating around. And it's all a little too bright to be necessarily the way you think food should look, but you're like, this is good, I like this. It says Kraft, I trust Kraft. So what do we think? What's that? Definitely a mixture. And would we call that a solution?
No.
No, why wouldn't we call it a solution?
Because you can see the difference.
You can see the parts. So what would we call it?
It's mechanical.
Very good. We call it a mechanical mixture. What's another word we might use for it? This one actually has a bunch of words that all mean the same thing. We could say mechanical mixture. We could say it's heterogeneous. Very good. Hetero meaning other. In this case, it means you can see the other parts. It's not the same throughout. There's actually one more word we use for a mechanical mixture, just to keep it super confusing. We sometimes also call it a... Did I mention this? I think I mentioned this. Maybe I didn't. We sometimes use the word suspension. Did I say that the other day?
I don't think so.
No? Oh, well, just so you know, I don't care. You don't need to know all three as long as you can use one of them, but be aware sometimes you'll see this word, suspension. But if you think about something being suspended inside of something else, you think of it kind of like just hanging there, right? So you can see it. Most often, you'll see this term, mechanical mixture. That's kind of the main go-to. Questions about that? Does that feel all right? Okay, I'm going to be quiet then. So now we're going to move on to 4.1c. I accidentally put a second 4.1c in. Whoops, sorry. I got excited. Science just gets me excited. I don't know what to tell you. So here we are, and we're going to get into it. But today we're going to look at how we identify or how we describe different matter, different materials, different stuff. Does that make sense? That's a big part of what scientists do. We like to look at things and we like to make observations. Do you remember way back in September? Oh, we were so young then, it's so long ago. Back in my day, September. Do you remember we talked about taking good observations? Do you remember that? What were some of the things we talked about when we took observations? We kind of dealt with two basic types. Do you remember that? Yeah, qualitative and quantitative. Quantitative dealt with what? Quantitative with an NT. Numbers, good. And then the other one, qualitative, dealt with qu'est-ce que c'est? It's me. Yeah, that's good. That's totally true. Qualities, descriptions, observations, things you can see with your senses, right? And that's what we're going to talk about today. We're going to talk about what we call physical properties, the physical properties of an element. And if you look at different elements, they tend to have different physical properties. Really quickly, if we were talking about stainless steel, could you tell me a few physical properties that we think of when we think of stainless steel? What's it like? Okay, it's stainless, sure, I'll take that. I mean, there's some in this room. I can see some right there. Describe it. What do we see? What does it feel like? What's it look like? It's hard. Yeah, it's definitely hard, right? You don't sleep on a pillow of stainless steel, do you? I wouldn't feel very good. Maybe you do. Maybe it's tough. Are you saying you do? You're like, I sleep on a stainless steel pillow. It's kind of tough as nails. It's shiny. Good, definitely. It's shiny. It's reflective. I can see light off of it. If I wanted to, which I don't, I can see my face in it. What else? Those are good. What about, here's an interesting thing. Everything in this room except you is basically the same temperature. Like I will tell you right now that that desktop and the steel side are the same temperature. I promise they are. But do a little experiment. Touch the wooden top of the table. Now touch the metal on the side. And I promise they're the exact same temperature. I promise. You can get them on. Guarantee you.
It feels colder.
Do they feel like the same temperatures?
I mean, the leg is a little bit colder because it's made metal.
Interesting. So even though they're the same temperature, and they are, that metal leg is able to draw more heat out of your hand than the wooden table is. You know, it's funny, if this room were really hot, which one would feel hotter? Right now the room's colder than you, and the metal feels much colder than the wood. If the wood and the metal were both hotter than you, which one do you think would feel hotter?
The metal.
The wood. Interesting. I'm not going to tell you. We can think about this. Though I'll say this. If you had to reach in and take something out of an oven, the whole thing's been in the oven, you had to reach in and pull it out, and it had a wooden part and a metal part, which part instinctively would you think is the one you want to grab to take it out of there? Well, we'll leave it there. But these are interesting properties, right? So even how quickly these things can take heat out of my hand and put heat into my hand. Hey, if you had to like disconnect the leads from a car battery, and you had the choice between a metal wrench or a plastic wrench, and you're dealing with the battery of the car, which one would you use?
Plastic.
Yeah, maybe you don't know, but if you do, what are you of course worried about if you're touching the battery of the car?
Electricity.
Yeah, you don't want to get shocked, right? And so metal will handle electricity different than something plastic will handle electricity. Yeah.
What if one is on fire?
Well, we'll get to that. So when we talk about physical properties, we're talking about the things that differentiate different materials, right? And you instinctively know this. You know what's interesting? If you watch a movie and you just see something on screen, Can you tell if it's metal or plastic or wood? Right? Just by seeing a picture of something, you can tell what it's made of. You might take that for granted, but that's actually kind of cool, isn't it? That just by quickly looking at something, you're able to see enough information to know what atoms it's made of. Kind of fascinating, right? You don't realize it, but your eyes are looking. They're getting enough information to tell you these are the little particles inside of this thing. Kind of neat. So we're going to talk today about what we call the physical properties of an object. Now, what do we mean by the word physical? What's that word mean? Yeah. To do with its actual substance, to do with the actual matter, to do with the stuff it is made of. And when we talk about a property, what do we mean? What's a synonym for property? What's another word we could use there? A word that's synonymous with property. Some properties, you could say some, what word am I going to write here? Traits, good. You could say characteristics. Ooh, boy, can someone do a spell check on that one for me? What's another word we could use? Am I? Look at me. Look at me spelling stuff right at 10 a.m. It actually helps that it's 10 a.m. Can I tell you something? In normal times, when I have to teach at 8 a.m., the spelling's real bad. It takes a while for the spelling to kind of warm up. Yeah. So there we go. So traits, characteristics, properties. What's another word? Oh, I had another one on the tip of my tongue, and now it's escaping me. Well, if anyone thinks about another good synonym for properties, I've got a space ready and waiting for it. What? Well, yeah, it's like if we're talking about a person, yes. Yes. Abilities is good. That's kind of a soft synonym, but I like it. Abilities. I have traits. I was all excited. I was like, ooh, we could say traits, but no, it's there. Okay, so here's the big idea. Physical properties tell us about an object, and we're often able to describe these properties using our senses. That should be pluralized. I want to go ahead and change that. So tell me, what are some properties? What are some traits? What are some characteristics we could look for? Yeah. Definitely. Shape is a really good one. Color is a good one, right? Take a minute. See what you can come up with. Fill in the space. I'm going to give you 2 minutes, and then we'll shout some ideas out. Talk to each other. Be friendly. Be a team. Shut up.
No.
Oh. Can I drink coffee? And I think we would drink coffee. Nobody wants to listen to that. You know, that sound of no, unpleasant. Can I ask, is the mic help, or is it annoying? It helps a little? Okay. If it becomes annoying, it's like because it allows me to speak at this volume. Instead of having to speak at this volume, and over the course of a week, that makes a difference. Right? You can do anything else that would describe something? Describe your shirt right now. Tell me everything you can about your shirt. Okay. Touch it like this. What's it doing? Touch that, then touch the back. How are they different? Cool. All right. There you go. That's good. That's a good one. Does this go to 5 after or quarter after? Quarter after, right? This class, it goes to quarter after, right? Like this block?
Yes.
Good. Okay, I'm right on schedule. Look at me. Look at me. Yeah.
You know what it's like to burn your retinas?
Do I what?
You know what it's like to burn your retinas?
But like, as in, like, when you look at something too bright and then everywhere you look, you see that shape again? Yes.
Do it all the time.
Yeah, I have done that a few times.
Your hair is green.
My hair is which?
Green.
Green. I was thinking yesterday that I might grow a mohawk. And my son suggested that I grow a Sullivan mullet. And then I thought, what if I grew a mohawk with a mullet? A mullet hawk.
I'm perfectly scarred by
Punk in the front, party in the back. I'm just saying. I think it's got potential.
No, mullets are like the worst thing ever. My stepsister's boyfriend has one and we all make fun of him all the time.
I like your
It just depends on
I want to go through my life knowing that I've had every possible variation of terrible haircut. And I think, and I've got a lot. Like I've thrown a lot in the mix in my life, but I feel like there's still terrible options I haven't pursued yet.
I had the worst haircut for about 8 years in a row, and I don't know why I kept getting it cut the same way.
Yeah, I've been having a bad hair millennium.
I would get it cut.
I would say roughly since the turn of the millennium, I've had unpleasant haircuts. Anyway.
I had very long hair, cut it to my shoulders with side bangs, then got it cut to my chin with side bangs for 8 consistent years, and it was awful.
I like it. All right, talk to me. What do we got? Shape, color, what else might we describe? Texture is good. I like texture. Excellent. What else? What did you have?
weight.
Weight is good. Weight or mass. Absolutely.
Material.
Does anyone, by the way, because weight obviously also depends on how much we have. Do you know what you call it, like how heavy something is given a certain size? In other words, say we had 3 bricks in front of us that were the exact same shape, but one was made of foam, one was made of plastic, and one was made of actual brick. They would all have different weights, but what do you call the property that tells you how much weight something has given its size? Do you know a word? It's a D word. How? Dense. Very good. Oh man, you guys are great. Yeah. What? Ooh, I like that. Like patterns in shape and things like that. Absolutely. What do you got? Ah, is it moldable? I don't know if that's a word, and if it is a word, I don't know if that's how you spell it, but we're going to put that there because I know what you mean. Definitely.
I'm saying it's wrong.
Usage.
Oh, what it's used for. Okay, I like that. Yeah, that's interesting. I wouldn't have thought that. Yes.
Texture.
Yep, definitely. We got that one on there. I like it. Yeah. Yeah, definitely. For sure. Yeah, but that's okay. That's good. What else we got? Ah, that's an interesting one. I'm going to put a little question mark beside that because definitely physical property, but then again, anything can be any different temperature. But you know what? There's something I really like. What about key temperatures like if you put water in the freezer, what happens to it? Freezes. If you put a bottle of windshield washer fluid in the freezer, what would happen? Would it? What's the whole point of windshield washer fluid? Like, why don't we just put water in our car thing to shoot up onto our windshield?
Because water freezes.
Because water freezes, so it just turned into a big block of ice inside your car, right? But windshield washer fluid does freeze, but it doesn't freeze at that temperature. So I would almost say one of the things about temperature I really like is what temperature does it boil at? What temperature does it melt at? Things like that. I like that a lot. Yeah. Ooh, reflective. I like that. These are really good. Wow, you guys are clever. Ooh, yes, definitely. There's a word for that. Sheen? Yeah. I think that's the word. If someone wants to Google that for me. I think sheen means shiny or glossy or dull. Yeah. Does it? Nice.
Material.
Ah, the material itself. I like that. Yeah.
What about the size?
Ooh, definitely size. So we could talk about length, width, depth, things like that, absolutely. And that's related to shape, but it's not the same thing as shape, definitely. Yep, I'm going to add that to the size bit. Those are really good. Those are all really good, yeah.
Length, or is that?
Yep, definitely. I put that as part of size, but yeah, for sure, length. Those are all really good. I'm trying to think. Yeah, I think you've actually covered most of them. You've even covered most of the ones we're going to talk about today, which is great. Durability is good. Yeah, because that is something you would note too. Like if you ever buy the cheap version of something and then you buy the expensive version of something, like the plastic itself, when you buy something cheap, you'll notice like, oh man, this thing cracks easily or scratches easily, right? And then you'll buy, like I used to have a set of like Craftsman tools, and they were fine, like they're great, but you know, they were probably 60, 70 bucks a piece at Canadian Tire. And then my father started buying me an expensive brand of tools like for Christmases, because my dad is like of the old generation where he like doesn't know how to express his feelings in any way except like buying you tools. It's just his thing, so that's good. I like it. I got a well-equipped shop. But so like the tools he would buy me, they're tougher, they're just more durable, right? Like you drop them, they don't break. They just kind of keep going. Yeah, definitely. If you're listening to this, Dad, hi, I love you. All right, so good. I'm assuming I had to write this before I could actually hear what you said, so maybe all your ideas sucked, but we're going to assume they're good because you're clever kids. Wow, I was being really whimsical when I wrote this. I was probably sleep deprived. Yeah. Oh, what do you got? Oh, very good. Yes, I like that. Sharp or dull. You know what? I like that for a bunch of reasons. There's actually a lot to like about that. One of the interesting ones, too, is that we've actually come across a synonym. Because when we said sheen, we really mean, is it shiny or is it dull? And then when we talk about sharp or dull, these words, same word, but they don't mean the same thing. I like that. Isn't that fun? What do we call those? We call those homonyms? Are those homonyms?
I haven't had that lesson since grade 2. I don't know.
Well, grade 2 was a lot longer ago for me than it was for you, kiddo. It was the 80s when I was taking that lesson. Yeah, that's right. That's right. People were wearing leg warmers when I was being taught that. Madonna was top of the charts, and like Cyndi Lauper. Yeah, okay, anyway. So here we go. So these are really good. So the main thing I want to take away is this, that we can describe a substance and identify substances by looking at all of their properties. Now, one thing to note, it's important not to just look at one of them, right? If I held up a piece of plexiglass and a piece of glass, if all we looked at was whether they were transparent or not, then you'd look at them and say they have the same properties, right? But if you came up and felt them, one of them will feel very sharp at the edges, the glass, right? Whereas plexiglass will never get that sharp. One of them will feel stiffer, whereas one will be more flexible. One of them will be easier to scratch, one of them very hard to scratch. So just saying one physical property doesn't really help us identify a material, but if you start to talk about all of their physical properties, you can nail down what a material is really specifically. Does that make sense? If you held up a piece of steel and a piece of aluminum, they share a lot of physical properties. They're both metals, so they can both be shiny, they can both be reflective, they both conduct heat, they both conduct electricity, they can both be sharpened, right? Like they have a lot of similar characteristics, but the steel is going to feel a lot heavier, right? There's going to be differences as well. Does that make sense? So you can't just look at one physical property, but if we look at a bunch of physical properties, we can identify what a material is. And we take for granted, but keep in mind, before somebody had written it down in a book, how did we know how many different types of materials there were out there? Do you know what I mean? Like, how did we know this rock and that rock are the same material, but this rock and that rock, oh, they're different? You know? And the answer is you have to start looking at them and saying, how are they similar? How are they different? It's a lot of work. Scientists did a lot of work just to identify what the different building blocks of our universe are. And they did that by looking at their properties. Does that kind of make sense? I hope. I pray. All right. I want to cover today a few of the key properties we're going to look at in this course. When I put something in front of you and say, give me some observations about this, here's what I don't want. It was blue. No, by the way, of course, there'd be like no capital letter there and no period. And maybe like that would be one of the better ones because a bunch of the other ones would have just said blue. And then I'd cry. You'd be like, what are these weird marks on the page I handed in? And Mr. Orlando has handed back to me. And I'm like, oh, those are his tears. He's weeping openly. Oh, except you're not giving me paper. So you'll never know. You'll never know the tears I cried into my keyboard as I mark your work of one-sentence answers. You'll be like, I wonder why Orlando's keyboard isn't working anymore. And it's like, it's recently been soaked in tears because of your lazy answers. That's why his keyboard isn't working. Yes?
On the keyboard, why wouldn't it be on the paper?
Well, because you're not giving me paper, right? That's because COVID. Like usually I will usually I can like circle it and be like, see these dots? That's my tears. Bad answer, kid.
That makes me sad.
Yeah. It's a sad state in life when the only thing that can bring me to tears is one-word answers in a science lab. But in all seriousness, when I say here's an object, I want you to take some observations of it, I want you to take good observations, which means I want you to look for certain key physical properties that we're going to talk about. And so today I want to look at some of the big ones. These are all really good. Like this is actually a great list. If every time we were told make some observations about this material, you talked about all this, you'd be like 100% scientist. You'd be killing it. And obviously you don't always need to talk about all of them, but like that's a really good list to draw from. I want to talk about some of the key ones today. And so here's some especially useful properties, and I gave you pictures, so that's exciting. Now this is one you mentioned. What do we call this? What do we call this? What is the difference? These are pennies. Ask your parents. These are a thing. These are a thing. I know, I'm kidding. Relax. All right, settle down. So yeah, these are pennies. These are American pennies. Who's that? That's Lincoln. That's right. Abraham Lincoln from Illinois. 16th president of the United States. Was he the 16th?
I don't know.
I want to say he was the 16th. Anyway, served in office from 1860 to 1865 when he was assassinated by who killed Lincoln? Very good, John Wilkes Booth. He was killed at Ford's Theater in Washington, D.C. So there we go. Here we have two of his likenesses on two pennies. What's the difference between these? Very good, yeah. So in this case, we're talking about sheen. And sheen, another word we sometimes use is luster. Have you ever heard that word, luster?
I have, but I did not know how to spell it.
Yeah, and if you're American, you'd spell it like this, but we're not, so we're going to spell it like that. If you say something has lost its luster,
That makes
really,
it look French.
lustre. It's English. It's English, I promise. But you see, I speak impeccable French. You just say things in English, but then you add an oh at the end, and people assume that you're French. I got it. Listen, I'm a francophone at heart. So when we talk about something sheen or its luster, we're talking about on a scale from being shiny on one side to being dull on the other. There is a numerical scale for this. So believe it or not, there's actually, you can get a device that will measure how shiny or how dull something is. You don't have to worry about that. Suffice it to say, shiny like a new penny, dull like an old penny. By the the way, why is an old penny not dull? What happens to it that it stops being shiny? Yeah, it oxidizes. So it will actually undergo a chemical reaction, but also just dirt, grime. Yeah, and a penny is copper, so if you let it oxidize fully, it will actually turn that amazing green color.
And then after that it goes black.
We actually do a lab in grade 11 chemistry where I have you start with copper, you have to rust it, you have to undergo a series of reactions, and then you have to turn it back into pure copper. It's a really fun lab.
When we went to Quebec, we had a whole lesson. We went to like a copper museum and had a whole lesson on it.
That's so cool. Did you guys go to Ottawa too?
No.
Because if you went to Ottawa in like grade 7 or grade 8,
Well,
COVID,
our
yay
school-
COVID.
Princess was, we didn't have like a lot of money, so we did one big trip.
Yeah.
And then one small trip, so we would have been going to Toronto, so we didn't miss
Well,
that.
Toronto's great too. Oh, I love going to Toronto.
I've done
Do you know Toronto's the 3rd biggest city in North America? Anyway,
Quebec was way better.
I love Quebec. I love Quebec too. But Ottawa's cool. But anyway, a couple of years ago they replaced the copper roofs of Parliament. So it's kind of cool because famously when you go to Parliament it's the green roofs. And then for like a brief period right now they're like actually like copper, which is really cool. And in no time flat they'll be green again. Yeah.
They're actually adding copper in Minecraft, and over like time it actually
Oh,
oxidizes.
that's cool.
Like 18 months, I think, or something.
That is cool. All right. What do we have here, obviously? What a crappy picture that is. I probably could have found a better picture, but here we are. I will say, I don't know why this person has windows that like get progressively easier to see through, but I like that he lives somewhere where there's a giraffe outside. That's all I'm saying. This is my goal. I want to have a house with oddly transparent windows and giraffes outside. I'm just saying, if I had a pet giraffe, I'd keep the windows open. I'd be like, put your head through here, Mr. Giraffe, I'll feed you. I want a pet giraffe, that's what I'm saying. I want donuts and a pet giraffe. Is that too much to ask? Okay, you probably know this word. If light is just able to pass through something, we say it is? Transparent, good. If light is not able to pass through something, we say that it is... What's the word?
I know it.
Ooh, can I get a spell check on that guy? Because that does not look right. I think it is right, but it looks so weird.
Yeah.
Opaque? So transparent, opaque. Does anyone know what we call it if it's a little bit transparent, a little bit opaque? Wait a minute, are you just writing transparent again? Very good.
Translucent.
Ooh boy, gonna need, is there an S there? Okay, let's get a spell check there. Okay, that's good. So there we go. So we know those terms. Having said that, what do we call this property itself? It may be opaque, it may be translucent, it may be transparent. Anyone here use Photoshop? In Photoshop, they would describe this by saying, very good, set the opacity. Or another word we sometimes use is optical clarity. Optical clarity. But yeah, if you use Photoshop, or even actually, if you, I think even in like Microsoft Word, if you just want to make a picture somewhat translucent, you can change the opacity on it. It's just a slider, and it goes between 0 and 100%. Yeah.
There's an opacity on almost everything.
Yeah.
Also on some drawing things, you can like change the opacity of the layers.
Yeah, in RGBA values, like in typical 16-bit color space, they call it the alpha channel. But anyway, that's a different thing. See, in normal colors, they use up to between 0 and 255 to describe how much red, between 0 and 255 to describe how much green, between 0 and 255 to describe how much blue, and then between 0 and 255 to determine its opacity, between fully transparent and fully opaque. Anyway, computer science lesson can come at a later date, but there we go. Nice. What do we have going on here? Yeah, obviously, one of these are both transparent materials, right? If we were describing their opacity, they're both transparent, and yet?
Durability.
Yeah, durability for sure, and flexibility for sure. And I'm going to go with the word flexibility here, because durability is a great word, but it includes a few characteristics. Because you don't have to be flexible to be durable, though if you're not going to be flexible, you have to be super, 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 super strong to be durable. Does that make sense? So if you get hit,
The material.
yeah. So in this case, we're focusing specifically on flexibility. All right, and that ranges from flexible to, what's on the opposite side of that?
Stiffness.
You could say stiff, or you could, I like stiff, that's actually good. But you could also even say brittle, right? Where instead of bending, it will break. Yeah. So these are all good things to be looking for when you find a new material. When you find a new material or when you're observing something, when we say make observations, you don't say blue. Unless you want me to cry. If you want me to cry, you can at least make me like happy cry, like one of those episodes of Queer Eye or something. It doesn't have to be like maybe sad cry, I'm just giving that answer. Sorry, one sec. If you see me reaching for the coffee cup without turning the mic off, please shout me down, because again, it's like right at like larynx height, and I don't imagine that would be pleasant for anybody. Okay, so now the next property we want to look at is an interesting one. What do we have here? Here we have like what looks like some kind of alcohol, water, something else going on, and then like what's going on here? Yeah.
Is it viscosity?
Oh, wow. Yeah, it is. Man, $7 word alert. Good job. That's right. Man, I didn't even have time to mentally prepare for spelling this because you're so on the ball. Okay, ready? I got this. I got this. Yeah, I'm feeling good. I feel good about that. All right. All right. So there we go. So viscosity is how much a liquid resists flowing. Oh, you did this last year? Nice. Did you all do this last year?
I just forgot what was
You guys are so on the ball. Again, like A+ job to your science teachers. That's great. Have you guys seen the longest running single experiment in scientific history? Have you ever heard of this before? It's called the pitch drop experiment.
Oh, I've seen that. It's like some like black liquid, right?
Experiment. Okay, so this is the most ridiculous scientific experiment in the world. And like a bunch of people have done this, but there's a famous one. There's a famous lab that has been going on since 1927. And this lab has been running continuously, so for almost 100 years. And there it is. And they have this black tar-like liquid in here. And since 1927, this liquid flows so slowly that only 9 drops have ever fallen. Now, 1927 to now, how many years is that? 93. So we're averaging a drop about every 10 years, give or take. About a drop every 10 years. And famously, in the 80s, they didn't have the camera turned on and they missed it. That's a true story. So famously, in an experiment where they only get 1 drop a decade, they missed it. Isn't that ridiculous?
How does it drop though?
It drips. It's just dripping out. The same way water would drip out of a really small hole in something. But this is such a thick, such a thick to flowing liquid that it just flows super slowly. Yeah.
Is the liquid called pitch? And is that
Yes.
why it's called pitch black?
Yes, that's right. Pitch, and for the record, they use, by the way, with anything, if you want something to be less viscous, if you want to flow faster, what can you always do with a liquid? And it will flow more quickly.
Put more water?
Okay, but then you're changing what it is. Without changing what it is, though that is true, definitely. Add heat. If you heat something up, it will move more. So like pitch is part of the same material they use to make asphalt. But to get that to flow, they have to heat it up. By the way, you've experienced this. Did your school have asphalt? Elementary school? And like, you know, on a really hot day you go out and it starts to feel like it's getting a little bit melty and liquidy? Yeah, it does, because you heat it up, it's going to start flowing. Anyway, so this pitch, if they were to heat it up, they could get it to flow quicker, but that's not the point of this particularly lame experiment. So anyway, the pitch drop experiment is right there, and I believe, if I'm not mistaken, they have a live video stream of it. Yes.
Is it still going?
Oh, you bet it is.
Watch.
Live streams is 1920.
So they think there's only about 8 years until the next drop, so that's pretty exciting. So guys, listen, if you log in now and just keep watching, you might get a chance to see that drop. There it is. See, here we are. By the way, why does it show that it is like almost 2?
Time zone.
Yeah, this is in Australia. So there it is. See that? And by the way, that looks like it could drop any second, doesn't it?
How is that 8 years away?
8 years to go. So there it is. Oh.
And that at the bottom of the vial is like 8-9 drops.
Yeah. Nice looking lab. Look at that.
Been in like the same place every.
What is pitch even?
What's in the vial?
No, they've moved it. So they use it again for like asphalt, for paving, for doing like tar roofs. It's an ingredient in like kind of tar-based things.
Where's in the vial next to it?
What's that?
Yeah, what's that?
I think this is actually like, as far as I can tell, this looks as though it is like in the hallway of the university. And I think they have like sealed bags of the material here so you can like pick it up and feel it.
Oh.
Kind of cool. Yeah, so this is like, this being world famous, it's publicly on display. So if it were like daytime, you could see kids like going into class here. It's like you wouldn't want to commit a crime here, because then all those like super sleuthy scientists like you guys, because I know you guys are going to be like my pitch drop experts now. And like, I'm going to look and I'm going to be like, what are you doing? Get off your phone. And you'll be like, where's Fernando? It could drop any second. And I'll be like, you get back to work, you. And like, yeah, I know. Your parents are going to be like, oh my God, all they do now is spend all day waiting for the pitch to drop. I get it. It's exciting. So I'm just saying, if you went to the University of Queensland, this would not be a good place to commit a crime, because like you'd totally be caught by like Orlando's science class. Yes, sir?
What if you get stuck in this kind of liquid thing? What is that?
Are you asking if you coated your body in this, if you'd be able to float?
No, it's just stuck in a pool of it.
That sounded weird again, didn't it?
What if you got stuck in a pool of it or something?
Don't. Please don't.
Drown?
What if someone
I don't
knows
know.
that?
I don't know.
I've got-
I just don't have a good answer to that, but let's just save ourselves some time and not. Yes. Yeah, here's the deal. I think, given how slowly it's flowing here, my suspicion is that it's got a whole lot of surface tension, and like you could probably get across it pretty good. But I don't know, not a material scientist, and I have never been dropped into a large vat of pitch, so I don't have a good answer to your question. Yes?
Answer Phoebe's question.
Sure.
Episode of SpongeBob where he skips it on the
Well, this has to be scientifically accurate then.
and then falls into
That guy lives in a pineapple under the sea.
Yeah. But he's a sea sponge, so
Yes.
it works.
Yes.
What if someone were to knock into it?
That person would make me angry. That's what. Okay. So anyway, I do want to mention, because it's easy to get what is high viscosity and what's low viscosity mixed up. You know what I mean? Because the word doesn't really tell you which one is which, right? Like, is this high viscosity or is that high viscosity? And that's why I specifically put the definition here, because the definition is how much a liquid resists flowing. So which one of these is resisting flow?
High viscosity.
Yeah, this one here is high viscosity, and this one here is low viscosity. And that's the kind of spectrum on which we live. Does that make sense? Yep. Yep.
Is that why it does it? Because of the viscosity?
Yeah, that's right. Is that the only reason why? I don't know. I have to think about that. Also not a physiologist, but my best friend is a professor of physiology, so I'm going to ask that question. But it's also why, like, in the winter, you have to put high viscosity oil in your car, you have to put low viscosity oil in your car because it's colder out. And so by nature, when things get colder, they want to flow less. So you have to put something that flows more. So like we here in Canada put a different oil mixture in our cars, and we don't change it mid-season, but we put one in our cars that handles the temperature range in Ontario well. If you bought the same car you drive here, but you bought it down in California or Texas, they would tell you to put different motor oil in. Because they deal with a different range of temperatures, and what they need to be worried about is on really hot days, it not becoming too thin and runny. So they use a higher viscosity oil than we do. We use a lower viscosity oil. If you buy a snowmobile, it's going to take a different viscosity of oil than will like a dirt bike, because they have different usages. Does that make sense? All right. What do we have here in this highly accurate picture? We have gold, and what have they done with it? They've hammered it down. In fact, gold famously, I have some in the lab. In fact, maybe when we go into 80 to do the lab, I'll pull out some gold leaf. I have some gold leaf in the lab, and you can get like a sheet of gold like this that doesn't actually cost that much money because it's very little gold. Because gold can be flattened into a sheet that is incredibly thin.
Is this one
Yes.
malleability?
Yes, very good. So the ability to be pounded into different shapes and to be bent into different shapes and to be flattened into a shape, we call that its malleability. And let's get that spell checking going on this one. Malleability. Gold, famously malleable. What about glass? Yeah, don't try to take a hammer to that piece of glass and flatten it out. That's not going to work real well.
No, try it.
Yeah, now anything becomes more just like things become more viscous, things also become more malleable as you add heat. This is why blacksmiths and until they don't work at temperatures enough to melt iron. And, through most of history, we didn't have the temperature to melt iron very effectively. But a blacksmith can still work iron, not by melting it, but at least getting it hot enough that it becomes more malleable. So the ability to be flattened or shaped, Iron is a lot less malleable than gold. It still is malleable. You can shape it, but it takes a lot more work. Has anyone ever gone down the YouTube rabbit hole of like watching people who make swords out of like, yeah, okay. So listen, if you don't, like get on it. But do you ever watch them, they use like the power hammer? So they use like the pneumatic hammer and just bash that thing down and it still takes forever? And then just be like, imagine having to do the whole thing by freaking hand. Like it's unbelievable. It's so much work. Steel is malleable, but it's not very malleable. If you did that same thing with gold, you'd do it a lot quicker. It's a lot more malleable. Now, you'd end up with something a lot less strong. Yep. Yeah. So there you go. Now imagine it was... Now you probably didn't make that, however, by taking a block of wood, heating it up in a fire, and then bashing it with a hammer. Or did you? No, because wood is not at all malleable. So you probably had to cut it on a saw, right? And then sand it, law sanding?
I used my stepdad's pocket knife.
Oh, you whittled it.
And then I shaved off pieces.
Yeah.
If I got a rough shape, I just sanded it until
Yeah. Yeah, with wood, because wood is not malleable, you sand, right? That is the story of carving things out of wood. Cut and sand more. So much sanding. Yeah, absolutely. I love it. Now, related to malleability is this one here.
Wire.
Yeah, the ability to take something and stretch it out into a wire is called its ductility, which if you think about it makes sense. If you like imagine what ductwork looks like, right? Like kind of tubing going all through. So ductility is the ability to be stretched out into a wire. That doesn't necessarily have to be a wire. I'm going to put a wire, but really the ability to be stretched out without breaking, but also without being elastic, also without snapping back. Right? You can stretch out an elastic band, but does it stay stretched out? No, it returns back to its form. Elasticity is actually another really good trait that I didn't mention here, but probably I'm going to just go ahead and put it up here because that's actually a great one that I didn't think of and none of you mentioned. What does it mean if something is elastic? Elasticity. Yeah, it can stretch out, and when you stretch it out, it will return to its original shape, right? Your skin is elastic, right? Like if you stretch your skin out, it goes back to where it came from. By the way, if you're dehydrated, low skin elasticity is a sign of that. If you squeeze your hand and your skin kind of stays in that shape longer than it normally would, that is a sign that you might be dehydrated. That's a free little tip for you. It could also be a sign that you aren't a real person but have been made out of clay and animated by some sort of mad scientist. I'm not saying that's you, but it could be. All right, a lab we normally do in grade 9, we probably won't get to, but we do one like it in grade 10, is we see how well different liquids do what? What's happening here? Very good. How well they conduct electricity. If you take tap water and you connect a light bulb through a battery, but you don't let the wires touch. So obviously if I touch this wire to that wire, the light bulb's going to turn on, right? But if instead you put the leads through the water, tap water, that bulb will turn on. Maybe not at full brightness, but it'll turn on. And that tells you that electricity can move through tap water. You want to know something interesting? If I take water out of the distilled water machine I have in the lab, and you do the same thing, you know what you see? Nothing. If you use pure alcohol, you know what you see? Nothing. But if you use salt water and really salt it, it'll glow at full brightness, just as if the wires were touching. So you can tell a lot about a material by how well it conducts electricity. If we took that light bulb and put one wire against the top of that table leg and the bottom of the table leg, what would happen? What do you think? That metal table leg. It'll light right up. It'll light right up as if you connect the wires. What if I put it on different sides of the wooden table? Nothing. What about the painting method? Yeah, probably not. Depending on the paint, maybe. Probably not. Probably not the insulation. Human body, that's a bit of electricity. Careful. More than we'd like it to. You ever electrocuted yourself? Yeah. I famously was renovating my house once with my brother, and I had turned the fuse off, and then at some point during the day, he was like, "Oh, my saw won't work," and he turned the fuse back on, and then I climbed up to the top of the ladder to install some lighting and shocked myself real good and fell on the floor, and I was like, "Oh my God." And so I went outside, I was like, "Ooh, that was scary, it hurt." It scared me a lot. And then you know what I did? Yeah, I totally forgot to go turn the fuse off, and I shocked myself a second time, because I am grossly incompetent. Just grossly incompetent. Anyway, the third time being the charm, I turned off the circuit, and this is why, this is true by the way, and the funny thing is, I'm like a safety officer. I take safety really seriously. Here, if I turn the fuse off, I have a whole kit in the back I go where there's a lock that you put on the fuse box. like a red lock that goes over the fuse, and you snap it on with a key, and it keeps it in the lock position, and you can only turn that fuse back on with the key. Like, I take that stuff really seriously, and then here I am in my basement just like zapping myself. So it goes to show that safety is important on the job, but it's also important in the home. You should just be safe all the time, not just when you're being paid to be safe. Anyway, that's a good message. So yeah, we call this electrical conductivity. Electrical conductivity. And that's just how well the material carries electricity. As a rule, metals tend to carry electricity really well. As a rule, plastics tend to not let electricity travel. Hey, what do we use when we make wires? We use metal on the inside, and then what do we use on the outside? Yeah, we use plastic or rubber or a polymer of some sort, the result of which is we give the electricity a path to follow. The copper moves really well, and then we surround it with a material that says, oh, can't go here. Does that make sense? Good, safe way to do it. Hey, electricity, go here. Don't go outside of here. It's a good thing, right? For cost purposes, we don't do that with all wires. If you look at the power lines that just run up above in the city, do they have rubber coatings on them? No, they're just bare wires. We trust that they're up there and elevated. My wife and I were in Haiti. We volunteered a couple of years ago and we worked, and a pole got knocked over and there was 2 live power lines just literally down on the street, just like sparking against one another and like kind of waving in the wind. And it was one of the most terrifying things I've ever seen in my life. And these guys had to repair it, but they didn't have access to the mains. It was a crazy thing. So they repaired this pole with the wires still. It was the scariest thing I've ever witnessed in my life. I thought for sure I was going to watch somebody get horribly injured or develop some sort of odd superpower. But they did it. They were really industrious, but man, it was scary because those wires are just the metal that says, hey, electricity, go here. None of that plastic or rubber or polymer coating that says, hey, electricity, don't go there. That's why it's totally safe for me to pick this wire up, even though it's got tons of electricity pouring through it, because it's safely protected. It is a conductive material surrounded by a non-conductive material. By the way, we call this one a conductor because it is conductive. Do you know what we call this one that doesn't conduct electricity? We could say non-conductive, not a conductor, but we also sometimes use the word insulator. Have you heard that word before? Probably you've heard it in terms of heat. Have you heard it before in terms of heat when we say it's insulation? When we talk about heat, we mean it doesn't let heat travel well, right? But it applies to electricity too. If something doesn't let electricity travel well, we call it an insulator. If it does, we call it a conductor. I should mention, this is actually one I didn't mention, but what if we had here a frying pan? Yes, that is a frying pan. Shut up. Okay, there it is. There's my frying pan. It's really good, isn't it? Yeah, it's a really good frying pan. I'm a very good artist. I'm doing my best. It's the best I can do. Okay, and then it's got a wooden handle, right? So there's our frying pan, and it's got a wooden handle, and this is all metal. See, look at that. It's all metally. Okay. Yeah, I'm a very good artist. So now, if we put a flame under this, would you want to touch that? No, that wouldn't feel very safe, would it? Right? Because that metal is a very good conductor. On the other hand, would you even want to touch here? No, because the metal is a thermal conductor. When I say thermal conductor, what is it conducting here? Good. So this applies to heat too. So even though here, we wouldn't want to touch it there because it'd be hot. On the other hand, would we touch it here? Yeah, because wood is a thermal. Very good. So we didn't talk about, I didn't actually put in the note thermal conductivity, but that's actually a good thing to discuss too. You could even put that below electrical conductivity, and you could draw your own frying pan. See how you do. Conductivity. The answer to that is I'm sure you'll do better because my frying pan does not look very good, but I did my best.
It looks like a red teardrop.
Well, that's because that flame heard a bad answer to a question about, like, describe this, and it just said orange. And it made it sad. There we go. The Bunsen burner. I'm doing my best. What do you want from me? I can't do any better. Here, and then a little blue.
Not be an art teacher.
Yeah, no, listen, there's no risk of that, I can assure you. So yeah, we can also talk about thermal conductivity, electrical conductivity, and then we've got one thing left. And we could talk about like softness versus hardness. So these are all the kinds of things we want to describe when we talk about physical properties, in addition to the obvious ones like shape and color, right? I didn't put a section here that says like shape. Do you want me to? And I can like put a triangle and a square and a circle, and you can all like describe them. But you all get shape, right? We all understand that one. And like color, I need to put a color one up there and say like this is red, blue. I'm a boy, so there's only 5 colors anyway. It's like red, blue, green, yellow, maybe purple. My wife uses words I don't understand, which she's like, this is fuchsia. I'm like, Sean. No, leave me alone. It's red. That's what it is.
Oh, it's not red.
Yes, it is. Yeah.
You know that riddle where it's like if you have 100 pounds of brick and you have 100 pounds of feathers, which one weighs more? And people always say, oh yeah, well the rock weighs more.
I like that.
Actually does it.
It's true. Now, having said that, if you had 100 pounds of bricks and 100 pounds of feathers, which one's going to take up a lot more space? What?
The feathers.
The feathers, you need a big old thing of feathers to outweigh 100 pounds, right? Whereas like a brick, just a few bricks, you can get to 100 pounds easily, right? Like what's a bag of concrete? You picture a bag of concrete, that's 70 pounds, right? So, a bag and a half of concrete's 100 pounds. To get a bag of feathers to weigh 100 pounds, I think it'd be a big old bag. Though maybe you could squish them down. How much do you think you can squish feathers down? Like, does anyone have a pillow that's full of feathers, like a down pillow? How far do you think you could squish that down? Like you have a pillow that's like normal pillow sized. If you really got to it, how squished do you think you could make it? You think about that big. Has anyone ever seen, I don't have one of these, but yeah? Yeah, of course. Has anyone ever seen, they sell these bags, like Ziploc bags for like your clothes or blankets or pillows or things like that, and you Ziploc your stuff into it, and that's got a place for you to put your vacuum. Has anyone ever seen this before? Have you? So I've always wanted to use one, I never have. But like if you put your feather pillow in one of those bags and vacuumed all the air out, I wonder how small you could make it. That's bonus points if one of you can do that. If one of you can Ziploc bag down a feather pillow and tell me how small it can get, you'll be my hero.
You know what? I'm going to talk to my dad and see.
Yeah.
Maybe one of those big Ziploc bags.
He might
I've always been fascinated by those vacuum down bags for like storing like clothes and stuff.
Should I bring it in if I can do it?
Yes, that would be super cool. Because I have like a vacuum sealer for my kitchen. Does anyone have one of these in their kitchen? You can buy it at Walmart for like $40. And it's just, you can buy like bags and it vacuums all the air out and that seals it. And that way you can like freeze stuff. And I like make soups and you can like freeze them really small. Or like if you buy like the Costco thing of chicken where you get like enough chicken to feed 72 people, you can freeze a bunch of it and just cook what you need. So anyway, I have one of these I use all the time. And it always blows my mind. My favorite thing in the world to vacuum seal is if you vacuum seal rice, it becomes like rock solid. Rice just flows, right? Like it just kind of moves, whatever, it's really soft. if you take a bag of rice and vacuum seal it, it's like a brick wall. You can't move. It's super cool. That's a dark thought. Why is that? That's your first thought. Could I hurt someone with this?
Yes.
That's the only thing you think of?
When we have apples to keep them like better longer,
Yeah.
it does nothing. We just go and then seal it.
Yeah, I think it does make a difference though. Get that air out of there, right? Anyway, so these guys, when we are describing things, hypothetically maybe, 20 minutes from now, these are the kinds of things we want to look at. Does that make sense? In addition to shape, color, is it a solid, is it a liquid, is it a gas? We want to talk about these things. Now, I'll stop the lesson there. Good job. There's a bit of homework